Welcome. It's day 4 of the Design Your First Earthen Tiny Home Challenge. We've already done 3 days so far, looking at different construction types for earthen construction, looking at floor plans, looking at structure, the roof structure. And today we're going to go into more detail with construction details. So if you're keeping up, I really celebrate you. If you're still catching up, I totally understand. I celebrate you too. It is very awesome to see the designs coming in the group. Please keep posting and sharing and asking questions. That's what I'm here to do this week, engaging and really helping you along. And I also understand, that I'm packing quite a lot into these 5 days. So yeah, there's a lot to digest. And especially today, we're going more into details. So if you've just joined the challenge, this might be a little bit advanced. I have tried to break it up with some nice examples, built examples, and also inspiration along the way. So by all means, keep watching, even if you just joined. And I would invite you that if you want to take part, that you revisit previous lectures so that it all makes a little bit more sense. And I'm seeing people starting to come on. Welcome. I would love to know where you're watching from. And just say hi. That is nice. I'm getting the hang of having a little bit of an eye on the chat. To hopefully catch questions and interact, and maybe just give me the heads up that you can hear me. And I will start with my presentation. So just to orient you, today I only have a presentation so that we have the visuals. We're not doing any further drawing anymore like in previous sessions, because now the designs will be quite different. But, all your designs will be quite individual. So I will start supporting you in the Facebook group based on your drawings. So I hope that works for everyone. Hi, nice, thank you. So yes, today we go into construction plans. So we go into constructive details. And I'm just putting this disclaimer up. I've done this every day just to, clarify that we can't give you legal advice on your building. You're responsible for what you're designing, especially if you're building it, and you have to check the legal requirements in your locations. And just really wanting to encourage everyone that ever watches this live stream, even in the replay, to whatever you do with your buildings, if you decide to not go for a building consent for whatever reason, either because you don't need one or because you don't want one, it is really, really important that you design to code. And that's what we teach. We teach earth buildings, safe earth buildings, to the New Zealand Earth Building Code. And the New Zealand Earth Building Code responds to quite stringent environmental conditions like earthquake and high winds and wind-driven rain. But it is an internationally recognized and cited document, so it is something we're very proud of. I've been involved in the revision of it and have quite a good insight into the whole document. So it is internationally relevant, and it's applicable to many places. So you can tweak it. You can, if you don't have earthquakes, you might not have to go to the length that we have to go here in Aotearoa, New Zealand, but it is a very common sense document, and it is very much written for self-builders and is very practical. So it's got two components to it. One is the design component, the other one is the materials and construction component. And the 1998 version is free for download. So always putting that out there because it is a really nice resource. And you will see in the group, most people are sticking to this. We're designing a 10 square meter cabin because of legalities here in Aotearoa, New Zealand, but also because we're starting small and we're learning the principles, and then it's easy to scale up. It's really good to have a plan, and you'll see why in this lecture as well. But by all means, design bigger buildings, like up to 30 square meters. If you want the same principles apply pretty much, there's a little bit more to consider in terms of bracing design, the stiffness of the building, but share them. And I think you might have seen someone in the group sharing big house plans. So that is one of our current students of the Earth Building Academy, who's showing you what he's achieved. He's done a lot of it himself. So they're actually also making bricks themselves and testing all the things that he's learned. So it's very exciting, and I'm happy that he is part of the design challenge too. So always nice to have returning students. And I'm also looking at you, Hannah. There's maybe a couple more of you coming back. So thank you so much for your ongoing support. And it's wonderful. It's like my Earth Building family is growing. So I hope you feel welcome in this group. So today we're going to look at the construction details. And I'm really inviting you into starting to imagine your room, your cabin in a three-dimensional way. That's one thing. And the other thing is that you start thinking about the detailing, so that you can be sure that it is stable, strong, well built, but the detailing is really important when it comes to weather tightness. So we are starting with the foundations. I'm sort of going ground up, and we have already talked a little bit about this yesterday, about the foundations, and I'm just going to recap that because it is very important. So you need to have good foundations, especially for your solid earth walls, but also for your timber earth hybrids. There's reasons why foundations are important. They transfer the load of the building into the ground and make sure that things like ground settlement, slumping, and so forth. So the stability really starts in the ground and really can make or break your building. And it's particularly important with the heavier construction methods, like even the low density adobe is still a lot of weight. The other thing that the foundation does is it raises the building out of the moisture of the ground. So if you look at the image, you see these minimum ground clearances. On the outside, there is a minimum ground clearance of at least 150 millimeters. It's often 200 or 225 millimeters, where you're, from the ground level outside to where your earthen wall starts. And that is to prevent splashback from rain. So, often there's that line at the bottom of buildings where rain splashes back. It's to also ensure that water runs away from the building and so forth. And you have the same thing on the inside in a smaller way. So the standard actually suggests that you elevate your earthen wall 50 millimeters above your finished floor level inside as well. And that is for two reasons. So it is during construction, when you don't have a roof on and it rains, it is to prevent rain that sits inside on your concrete pad or your floor during construction to wick into the bottom of the wall. So also during construction, that whole wall is raised up, and it is also in use in case you ever have a burst pipe or something, that there's no risk of water ever penetrating into the base of your wall. It's not so relevant for a little cabin because legally you're not supposed to have any plumbing in this building, but depending on where you are, you might be able to put plumbing in. And I have actually personally had the situation where I think it was a washing machine burst, and there was a big flood inside the building, and it wasn't an issue because of that little nip. So that's part of the foundation. And then very important again is that the top of the foundation gets painted with a bitumen paint to prevent moisture wicking up through the concrete and into the base of the brick. So here you see, what I've been the fall away from the building and the little nib inside. So that's foundations. And for your the timber foundations, I showed a detail yesterday. It's the same kind of principles. The foundations are just smaller for the timber earth hybrids. And you would be looking at the timber frame standards to choose the type of foundation that would suit your construction method. And in terms of what kind of materials can be used for the foundation, it really depends where you are. So in Aotearoa, New Zealand, where we have earthquakes, the simplest solution is a concrete foundation, steel and cement foundation. It's probably the only place where I I am for cement. Like, I don't like mixing cement with any other component of the building, pretty much. It makes a lot of sense in ground. It's a simple solution that is easily engineered. There's other solutions, of course, but they need to be overseen by an engineer. So things like using bricks or concrete block or all those solutions probably can be done, but they are not what we call a non-specific design. So they are specific engineering design that would have to be checked by an engineer. And in countries where you don't have earthquake, you have a little bit more flexibility. So, you can go to a rubble trench foundation or a stone foundation and be safe. That's good. So you just have to really check that your soils can handle the weight. So the type of soils, sometimes the site has to be assessed for that. And then you need to understand what the requirements are in your location in terms of depth of foundation. In some places where you have frost, that changes, and if you have earthquakes, it has to be taken seriously. And the other thing is, because in earthquake zones we're working with steel that comes out of the foundation and into the earthen wall, that is like it's actually like, you could argue that you could maybe substitute the steel for other materials like bamboo or so, but the combination of the steel and the concrete is a very strong material combination. So there's not an easy substitute for those high carbon materials, unfortunately. And I'm just seeing here the comment that there's no earthquakes in Northland, so that is great. You're still a part of the, you're still living on an island that is on the Pacific Ring, the Great Ring of Fire. So, and you're probably more exposed to very high winds, so destructive cyclone type winds, and wind force and earthquake forces in some instances are comparable. So when we come to structure, like when we were talking about the structure, the strength of a building, it's not just earthquake. Wind forces are substantial, and they can and do damage buildings, earthen buildings as well. So it's important to keep this in mind and to comply with the standards, because the standards are not there to be a pain in the ass. They are there to keep people safe. Okay, so that brings me further up. So another place where we would be typically looking at is wall-to-roof foundation connections. And the roof-to-wall connection is also very important. I've just mentioned wind, so like the fixings. We talked about this yesterday. When you're specifying the timber sizes for your roof members, there's always a mention of the type of fixing that you need to put in, and you need to follow that, because wind uplift in high winds is a serious thing. So there's always the situation where roofs blow off. you need to take this seriously. So follow the standards according to your wind zone, and I would even encourage you to overachieve a little bit with this and go for the next wind zone up, because wind strengths are picking up in most locations with changing climate. I want to show you the details for the roof from a point of view of weather tightness. So you're mostly dealing with a timber structure when you're looking at your roof. So regardless of what your walls are made of, you're likely to put on a timber roof. Some locations on the planet, this is not the case, but we're just assuming it's a timber roof for the sake of this training. And depending on the shape, we looked at the monosloped roofs, which you see on the slide here, with just one plane going from the front to the back. There's the gable roofs. The different situations with the roof shapes will have different points that are vulnerable to water ingression. So if you look at this drawing here on the slide, this is a section through the roof. So it's like cutting the building in half and looking into the construction and seeing what is happening. So you have, cut timber where you see these X's. That's here, that's the top of the wall here. And then you see under the roofing, you see the little cut pieces of timber that are your purlins. There is places where water could come in. And if you think about it, like the rain hitting the very front of this roof, for example, it runs down the front of the roof, and then it's detailed so that most of the rain drips off. The board at the front is called a fascia board. Might drip off, but it could also be blown back onto the underside of your roof overhang and then run towards your building, because in this monosloped roof you have an inverted, a reverse slope eave. So in that case, this little see the little black thing that connects the roof to wall junction protects from water ingression. So that is called a flashing. It has a little drip edge, and it protects material junctions from water ingression, because especially if you have wind with your rain, water just has a way of finding its way into the structure. So these flashings are very important. They are an added cost, but they really are recommended. Same thing at the top of the building, the very top. You see the black line that covers, that sort of protects the very top of the roof where there's a material change from your roofing iron to your fascia board. So everywhere where you have material changes, you have gaps, and you need to apply these flashings for water to keep out of your construction. Here is another overhang, so another eave, but this is not a monosloped roof. It's this one side of a pitched roof. So you see that the situation is different. It's not a reversed sloping eave. It points down towards the ground. And if you think about rain hitting this wall, it will just flow down the roofing iron and then be caught by the gutter. There's not much risk that it will be pushed back up along the rafters and towards the top of the wall, So you don't need a flashing in this situation. You just need a gutter. Hope that makes sense. Yeah. And then in terms of roof overhangs, so we already touched on this yesterday a little bit, and I'm just seeing that the video has frozen, so I'll just let that buffer a little bit, and maybe someone can give me a thumbs up or a 1 if you still hear me. Thank you for letting me know, Tom. Just give me a sign of life if you can still hear me. Yes, good. Your reactions also come through delayed, so there's just a little bit of a lag. This is what happens with streaming. Okay, so back to roof overhangs. So in any building, it is a good idea to have roof overhangs because the roof overhangs protect the walls and direct water runoff away from the walls. So the water can then not hit the walls directly all the time. Like in big weather events, you will still have water on your walls, but in sort of moderate or light rain, you just have that good height. They are particularly important for solid earth walls that are designed to the earth building standards. The earth building standards assume that your material, so the actual earthen material, and the design together ensures weather tightness. So you can't rely on surface coatings, not even plasters alone, to give you weather protection. So some people want to apply silicones or even lime plasters, which are more compatible, but you can do that, but you can't solely rely on that. And the way that the New Zealand standard looks at the weatherproofing equation is that you take into account the erodibility of your material. So that's a thing for another. I actually have done live streams on this as well, but the actual building material is tested before it goes into the building. And one of those tests is an erodibility test. So the results from those tests will give you an erodibility index, which informs, this is the EI in this table. So it flows into the equation. The other thing that is looked at is the wind zone. So, there's different tables for different wind zones. And then you have you need to understand how, you have to take into account how tall the walls are. So the taller the walls, the more exposed they are and the bigger overhangs they need. So let's say, you have an erodibility index of 1 or 2 here, and you have walls that are 2.4 meters tall. You can go in here, read up and then across, and then it will tell you the amount of overhang that is required for your earthen building. This is for high wind zone. So you see that quite big overhangs are required in high wind zone. So there was someone in the group saying, I have a building, it's on top of a hill. You will be very exposed to wind. So think about constructive weather protection for your earthen building. Could be a thing like a veranda roof, or it could be a zoning, like a little sunroom on the front, or it could be a rain screen or something like that. But this is, I'm just putting this in here to invite you to have a look at the earth building standard if you're designing an earthen building, even a small one, and start thinking about how big your roof overhang has to be. And then another detail that is very common is this earth wall to timber frame connection. So let's say you have a gable roof like this. Your walls, they finish at a certain level, and then your roof is a triangle on top. The gable end is that triangle. So you will have a bit of timber in there. Or let's say for your tiny house, you're designing for a little sleeping loft or something, there's a little bit of timber construction above the earthen wall. And from a structural point of view, that is absolutely possible. Earthen walls can support an entire upstairs story, but there's a material change. So where the yellow mark is on the image, you see where that material change happens. You have to understand how the rain hits the timber frame and how it wants to flow down. And then you have to divert that rain away from the face of the earthen wall and prevent it from going into that gap. So there would also be a flashing with a drip edge. So pretty much for your design, just think where are there material changes or gaps? And in those locations, you will have to sort out flashing and ask questions in the group. Like if you're starting to think about how that all goes together, um, ask questions, or draw a little sketch of what you're trying to solve. I'm putting in a couple of I've put in a couple of images here. They're bigger buildings. The bottom right one is a small house. It's a 30 square meter building, but I just wanted to show you what I'm talking about. Like up the top one has got that gable end with a timber situation that hangs over the mud brick a little bit and has a flashing so that water can really drip off. These people designed with minimal roof overhangs. Their bricks were very good quality. So this building has done really well, even though there's actually minimal roof overhangs. The minimum, I think, the minimum is 600 millimeters roof overhang for earthen, like solid earth walls. I would suggest you go for at least 900. And it's also, something that you want to optimize in terms of your sun angles, shading summer sun and letting winter sun in. So really encouraging you to think about roof overhangs for more reason than one. So one being the weather protection, but the other one being shading, because shading is important. Like little tiny houses actually overheat. So it's not just about them being warm, it's also about them not being too hot. The bottom left is our building. So we have a load-bearing solid earth walls in the ground story, and then we have a timber frame building. It's a timber earth hybrid at the top. And I've put this one in because you see that reverse slope of the monosloped roof. So any specifics for green living roofs? There's just a question that has come in. The only thing that I'm saying, like when you're designing green roofs, you have to follow the whole way it is built up, like the layers and everything. So that's a whole story for in itself. But as it relates to the earthen buildings, is that with a living roof, you're dealing with a heavy roof construction. So you have to allow for the weight. And when you're sizing timbers, when you're looking at the timber frame standard, there are tables there to size the timbers for heavy roofs. So that's probably as much as I can say about it right now, is that certainly you need to keep the weight in mind. And there's still flashing details with all of that, because whatever type of roof you have water runoff at some point. So here you see another building, a small building that was built by another one of our students. And I put this one in to just show you again the gable end here, and how they made the roof big enough to have an upstairs sleeping situation. And the other thing that they did is attach this little veranda at the front, which is covered entry space, and it protects that front earthen wall. So I think they did a very nice job of just solving this. So it's an example of what I mean with constructive weather protection. Constructive weather protection means there is some kind of structure that additionally protects the earthen walls, and the earthen walls do not have to have a protective finish layer. They can, and often it makes sense to have one, but you're not solely relying on this finish layer to give you water tightness. So often, people apply, it depends how exposed you are, but like often there's lime plasters that get applied to the exterior. They work really well. And there's a whole, actually, if you go to our YouTube channel, there's a whole series of lectures that I have done on weatherproofing buildings and maintenance. And breathability and so forth. So the whole exterior, the finishing, the exterior finishing of the buildings is covered already on the YouTube channel. So another couple of images of very small buildings. I mentioned Mark Fielding's work with the pellets before, and here you see that he actually built these panels. They were prefabricated panels made out of pellets that then were put together. They were used in all three dimensions of the building, for the walls, for the floor, and for the roof. All reclaimed materials from the waste stream. He used styrofoam as an insulation. We have used light earth infill in this system and much prefer it because of breathability considerations. And then the inside, to the bottom left, you see how he finished the inside. He used recycled carpet, has inside out with a clay paint. We have done the same, but instead of a clay paint, we have used earthen plaster to finish off this type of building. And it worked really well. He got a bit obsessed about this, the little posse, he called it. So he had a few different designs, and I just wanted to show you. So the bottom left one it was part of a project called Gap Filler after the Christchurch earthquakes. All of these materials in this building have been salvaged. So there were things like printer from the press, newspaper press, metal sheets and reclaimed timber and whatnot. And they really sort of demonstrated waste stream use of materials in this one. And then the other one just had slightly different roof situations for tiny living situations or extra rooms. So yeah, I like his work. On his website, there's also architectural drawings for bigger buildings that you can actually look at them like on the screen and just get inspiration. And they're also for sale, very cheap. And he's one of the designers with whom we work with the most. He's very into passive solar design and also bringing costs down. So I'm wondering, shall I show this right now? Yeah, let's just go over to this for a moment. I just wanted to show you something that I saw online yesterday. I go down these little rabbit holes. So this is something that has been done in Australia. So these are plants that you can buy, and it's actually exactly what we're doing. So it's a 10 square meter building, and they just sell these plants. In Australia, apparently you don't need a building consent for this. Like, I think it's the same thing here in New Zealand, Aotearoa, New Zealand. And I just wanted to show you how they solve this, because it's a different solution again. So it's surprising and awesome how many different designs there is, even with this really small footprint. And the reason why I'm putting this in, apart from just showing yet another solution of how to organize space, is because I wanted to explain something in terms of architectural drawing or like sketching. So if you look at the image in the middle, or let's go over the top right one, that's your floor plan. That's what you've been doing. The one in the middle is called a section. So it's cutting the building down the middle from the roof down into the foundation and really drawing everything out. So your roof, your room height, the size of the timber for your sleeping loft, for example, the size of your timber for your roof, because all of these material sizes and room heights and head clearances and stuff add up to the overall height of your building. And you need to check that, and then you can, if you sketch out your building in a section, you can also check things like heat clearances. You can check if the roof somehow gets in the way, or the roof overhang would get in the way of your view, stuff like that. So encouraging you to at least start thinking about your building in a three-dimensional way. And I'm just going to see if we can click over. There was something else that I want to show here. Here. Oh, yeah. This other way of depicting, that's looking at the building from outside. So again, like you're just looking at the building. It's a two-dimensional depiction of the building, but it takes into account the height of the overall building, the height, where your windows are in relation to the floor, how much your foundation takes up. So it's that third dimension, like the vertical dimension, that we're starting to look at in today. And I just wanted to show you this so that it is clear what I'm talking about. This is called an elevation. So when you're looking at a building from the outside, an elevation, it's basically each side of the house, how it looks. And the thing I showed before is called a section. So please let me know if this is clear, what I mean by elevations and sections. If you have questions, pop them into the chat, and we'll just circle over to a few more details. So talking of sections is, it's like dissecting, it's cutting. Let's imagine that we're cutting through a wall and we're looking at the situation at the top of an opening. So here in the middle, you see the thing with the crosses, the light colored thing, is your timber lintel, the thing that spans over your opening. It's not very common that you have mud bricks above the lintel, but sometimes you do. But the reason why I've put this in is because I wanted to show you that at the top of the window, it's another place. So if this is the lintel and the window comes up against it, it's another place where there's a material change and a gap. And it is typically where you could have a leak, or, where it's not weather tight. And I'm just pointing out the right side of the image is the outside of the building. And you see at the top there of the wooden window below your lintel, there's a flashing. So the top window flashings are very important. And it's often something that I see is missing when people just build their own stuff. They just put in the windows and they don't think about the top flashings, and it's important to put them in. This here is different. So this is the side of the window, and this time we're cutting horizontally through the wall. We're looking down onto the windowsill, and we're looking down onto the window horizontally, and looking at how is the window joining the side of the mud brick wall. So here. And you see again, like there's different ways you can do this, but ideally you have a little bit of a step. You don't need a metal flashing there, but you need a board that covers the gap between your wooden window and your mud brick. In a timber situation, it's different. We'll go to the timber in a moment. But this is called a side flashing. The flashing can be made out of, it's often made out of metal. Sometimes wooden flashings are enough. And looking down faintly, you see the windowsill. The windowsill is also really important. It's like your bottom element that directs water that flows down the window away from the wall below. So windowsills are also really important. Just going to show you a windowsill from the side now. So again, that's cut vertically through the window. You see the bottom, like the wall below the window, and the sill. And you have to have a sill that sticks out over the face of the wall enough so that water can really drip off rather than sort of flowing back onto the wall. And this is typically something that I see happen is you set up, like people set up the windowsill, but then they later plaster, and then the windowsill doesn't stick out enough anymore. So when you're building, think about whether or not you want to plaster and really install a windowsill that has this minimum 50 millimeter overhang, which ensures that the water actually drips off. And you have enough fall, and the windowsill is made of a material that can handle the water and so forth. Okay. So believe it or not, the details for the earthen, like the solid earth construction, are simple. The timber frame construction details are more complicated. So especially if you're based in Aotearoa, New Zealand, I would encourage you to have a look at the relevant standards. So the links are in here if you want to look them up, because there's quite a lot of different details, and I can't show them all to you. I'm also, my main thing that I teach is actually solid earth construction because it is simpler. And I'm not a carpenter, but go and have a look, and wrap your head around how timber construction works if you're going down that way. Because the timber construction, you already see this, has many more different materials in layers installed. And the timber construction, if you have ingression of water, you can get rot. That eventually will destroy your building, so it's not safe from a structural point of view, but it also creates a real big health hazard. So you don't want to have a leaky building at all. And the timber is actually, in a way, not more problematic than the earth, but if the earth gets a little bit wet, it just dries out. It never rots. It doesn't grow mold. But as soon as you have woody materials or light earth materials or anything else in layers, you need to take this quite seriously. So here I'm just showing you, it's quite nicely done. This detail, it's easy to understand in this more three-dimensional way. They've drawn it. The head flashing at the top of the window here. That goes behind the timber cladding and then protrudes over the top of the window, so that you imagine if water hits your cladding, the outside of your wall, it can just flow down and then drip off along that flashing. And here are some sill details. So again, there's different situations with timber construction for the sills, but one of these is just to put in this sill flashing underneath your timber window that then allows this junction between the window and your cladding to be weatherproofed. So this is the same thing, just in a section. So if you're not used to reading architectural plans, it will take you a little while. I would suggest you start with these three-dimensional, colorful depictions, and then you start understanding which element is which, because many of the architectural plans are then, like depicted in a two-dimensional fashion. So like these sections, what you see here again is the head flashing over an aluminium window. So you see it in a two-dimensional depiction cut through. So you see how the head flashing goes behind the timber, it's attached to the timber frame, and the cladding goes over it. And you see how there's quite a big gap behind that where water could penetrate. So you see why it is important to put that steel flashing in. Yeah, and the question about how to draw this and how to figure it out, I'm not saying you need to get all of this down for the tiny house challenge at all. I'm just starting to get your mind going around problem solving and understanding, that you need to have flashings around openings as a minimum in the roof. So those are typically the two really important places. And that you start thinking about the building in a three-dimensional way. So that you start going, how tall is the room? Where does the roof go? If I have a gable roof, how tall is that? What kind of timbers am I using? So that you really can check things like head clearances. It's a typical mistake, that all of a sudden you go, oh, this window is too low or the door doesn't fit or something like that. So you need to really start putting the whole thing together in a three-dimensional fashion. And in terms of the challenge, we're going to keep it kind of simple. I'm just going to invite you to think about the outside of the building. So all four elevations, all four sides of the building. Based on your floor plan, you've put in doors, you've put in windows. Think about where are these windows in the elevation? Think about how big they are, how tall they are, and draw the elevation. Draw all four elevations for your tiny house. And that will allow you to calculate the wall area. So far, we've only looked at the floor area of 10 square meters, but we want to know the wall areas. So all four sides of your building, the area will be, the length of the wall and the height of the wall multiplied minus the windows and doors, minus the openings. So draw it out, make a list of the sizes of your doors and windows, make a schedule that includes the measurements, calculate the wall areas, and share that in the group, because that will help us tomorrow when we do a little bit of quantity survey. So I hope it's getting denser in terms of all the downloads and so forth. I'm very happy to take questions right now, or for you to go away and wrap your heads around this, and then come back to the group with questions. So I'll just have a quick look at the chat. If anything comes up right now, put it in the chat. And I think I sort of caught the questions as they came in. Yeah. So if you have anything else, pop it in right now. Otherwise, we'll see each other in the group. And I'm looking forward to seeing your elevations. And I think, again, don't overthink it. Just start with a concept drawing of how you imagine the side of the four sides of your building to look. Put it on paper, and then if there's anything that needs to be troubleshooted, we can do that based on what you've drawn. So I'm looking forward to seeing what you come up with. And that concludes the fourth day. And tomorrow we will look at some logistics and a little bit of quantity surveying, which, the design process is always, that's why you're doing concept drawings and not exact architectural drawings right now, is because you have an idea, and then you look at the material sizes and you start pricing, and then you tweak until you've optimized it for what you want to achieve in terms of design, costing, and so forth. And then you make the proper architectural plans should you need them. For a 10 square meter building, you don't. You just have to have good sketches. Okay. Thank you so much, everyone. I look forward to seeing you tomorrow. Bye.